continuing looking at circular motion, we've looked at the ideas of centripetal force and centripetal acceleration. We're now going to have a look at some specific examples where centripetal force is at play. You can see here I've started off with a diagram of a satellite around the Earth. Just to speed this up, I've produced some diagrams already that we'll have a look at as we go through. So the idea of the satellite's orbiting Earth, you can imagine that it's going to be on this circular path that travels around the Earth, and it will be moving in that sort of orientation. So the velocity at that point in time would be out to the what looks like to the right on the diagram, and so here the centripetal force would be directed towards the center of the Earth. So the centripetal force here, so just on the right hand side, I'll indicate what the centripetal force is for each situation. So the centripetal force in this situation is provided by the gravitational force. Now gravitational force would usually refer to that as being the weight of the object, so in this case the weight of the satellite. Now the acceleration due to gravity at the altitude of the satellite is not actually 9.81 meters per second squared. We'll look at that in more detail in subtopic 6.2 on Newton's law of gravitation, but we would consider it to the weight of the object that's actually providing the gravitational force in that scenario of a satellite orbiting the Earth. In order to figure out the speed of the satellite, we'd need to know something about the altitude, so we'd then need to add the altitude. So the altitude would be this distance here, or the height. We'd then need to add that to the radius of the Earth to get the total radius of the path of that satellite, and we'd need to know what the period is, how long it takes to orbit the Earth, and then we could figure out its orbital speed. The second example that we're going to have a look at is amusement park rides. There's two here that we're going to have a look at, and this one you may or may not have seen this before. This first example, I've known it as a gravitron. It may have different names depending on which amusement park you go to, but with a gravitron, basically what happens here is that this whole structure is sort of spinning with some angular velocity. And as a result, the people that stand against the wall inside, they're moving at this point in time. This particular person would be moving at a tangent to the wall, so they'd be moving to the right at that point in time, which means that the force that would be acting on them is towards the center of rotation. So that would be the centripetal force in this case. Now the centripetal force that's providing that's causing the person to move in a circular path here is actually the wall pushing on the person. If you think about Newton's third law, the person would then be exerting a force onto the wall as well. So there's that application of Newton's third law there. Keep in mind here also that there would be some friction. So one of the things with this ride is that usually once it starts spinning at a fast speed, the floor will actually drop away and you'll be pinned to the wall. So friction also can come into play there, so that stops people moving vertically. So there's the first theme park ride that we're going to have a look at. The second is the good old chair swing. So the second example of a theme park ride. So with a chair swing, there are actually only two forces that are acting on the person. The first is the weight of the person that's pulling them down, and I suppose two that the second one is really the force of the chair pushing back up on the person, but that's really provided by the tension in the cables themselves. So the weight pulling down and the tension in the cable. So they're the only two forces that are really important here. What that means, though, you can see that the tension's not directly opposing the weight. There would be a vertical component of the tension that balances the weight because there's no vertical motion once they're moving in a constant horizontal circle. But there would be a force, an unbalanced force resultant force, I suppose, so we could actually call this three different things. The resultant force there would actually be equal to the horizontal component of the tension, so TH, and that will actually be providing centripetal force. So as this person sort of is swinging around, so going away from us into the page or into the screen, the centripetal force that would be acting on them would be to the right, and so they would then follow a circular path. So in this case, what's providing the centripetal force here is the horizontal component of tension in the wires. And if you think back to, I think it was subtopic 2.2 on forces, you could go through and calculate the weight and figure out what the tension is, and go through and figure out what that horizontal component of the tension is to determine the centripetal force. The next example is looking at cornering in a car, or turning a corner. So with turning a corner in a car, so we're looking down on top of the car here, so you can see the angle of the wheels there would suggest that the car is turning in this sort of direction, so that would be the path that it's travelling. So at this specific point in time, the velocity of the car is forwards, and so its velocity will be then changing according to the path that it's travelling. And we know that the centripetal force that acts on a car, I'll just draw this further through the centre of mass, centripetal force then has to be perpendicular to that. So the centripetal force here will be directed towards the centre of the circle, and the centripetal force here is provided by friction between the tyres and the road. And again, if you refer back to subtopic 2.2, you can actually identify here that if we're dealing with friction providing that centripetal force, we know that the centripetal force is going to be mv squared on r, but the friction force is the force that's providing it here, providing that centripetal force, and we know that the centripetal force, the frictional force, is given by the coefficient of friction multiplied by the weight of the car, or the mass times the acceleration due to gravity. Now there is an upper limit to that force due to friction, so this centripetal force has to be less than that frictional force, or the upper limit to the frictional force, to avoid the car skidding off. So skidding off the circular path and say driving into off the road or into a barrier or whatever it might be. So we can relate the centripetal force there back to frictional forces. Now, turning a corner can be made a little bit easier with the next example, and that's looking at banked turns. So with banked turns, what actually happens here is the road is now on an angle. So you can see that we've got this angle here between the horizontal and the road surface. Now, these sorts of situations you usually only see in, NASCAR over in the States, or those sorts of motor vehicle sports where you've got a banked turn. Now again, there's only two forces acting on the car here. The first is the weight of the car pushing down, and the second is the normal force pushing up from the road onto the car. Now again, those two forces, you can see that the weight force, if I drew it a little bit more to scale, the weight force would be balanced by the normal force, which gives us a resultant that acts in the horizontal direction. Now that horizontal force is the horizontal component of the normal, and again, if we know the weight, we can figure out the vertical component of the normal. So if we know angle theta down the bottom here, that's going to be the same as the angle that the normal is away from the vertical. So we can use trigonometry to figure out then what the resultant force is. That's the normal component of the horizontal component of the normal, and that's actually providing the centripetal force to keep that car moving in a circle. So in this example, the centripetal force is going to be provided by two things. So there'll still be some friction between the tyres and the road in this scenario, but it's also then the horizontal component of the normal force. Now, what you can see here, given that some of the normal force is actually providing the centripetal force, there is an advantage to having a bank turn in that it allows faster cornering. So because some of that normal force is actually contributing to the centripetal force, the speed with which you can move around the corner, V, is now a little bit faster, and makes it a bit quicker to get around those bends. Means you don't need to brake as much, so there's some significant benefits there. The next example, looking at athletics, a few different events where centripetal forces come into play. The example that we're going to look at here is the hammer throw. So in order to throw the hammer, which is basically this large mass at the end of a wire, the athlete would spin around, and so let's say this thing's moving in a circular path, going around this way, and so it's sort of all the way out here and come back around again. So the velocity at this point here is going to be going sort of away from the observer, or us as observers. So I should mention here that this whole system is going to be moving with an angular velocity. So the force that's being provided at this point is going to be due to the tension in the wire itself. So that tension here provides the centripetal force to keep that mass, or the ball at the end of the chain, moving in a horizontal circle. So there's a few examples of circular motion and the types of forces that are providing the centripetal force, and you can see that they vary quite a lot depending on the scenario, and in some cases you can link back to some of those ideas from subtopic 2.2 on forces in order to actually calculate what the centripetal force is.